When we need to securely encrypt large volumes of data, like a streaming video or a database backup, we rely on symmetric block ciphers, like AES or triple DES. They are the standard for high-speed confidentiality, engineered for maximum data throughput. But these systems operate on a strict mechanical constraint. As this diagram shows, both the encryption algorithm, EK of X, and the decryption algorithm, DK of Y, utilize a single identical secret key, K. Provided that key is long enough, the resulting ciphertext is mathematically secure against brute force attacks. The weakness here is not mathematical, it is logistical. It is known as the key distribution problem. For this protocol to function, Alice and Bob must both possess the exact same secret key before they can start communicating. If an adversary intercepts that key during the initial transfer, the entire system is broken. Security depends entirely on a single vulnerable event. This constraint is manageable in isolated environments. If you are encrypting a local hard drive, the key distribution happens physically, right at the hardware level. Symmetric encryption solves the problem of data confidentiality, but it shifts the entire burden of security onto the problem of secure key transport. That transport problem becomes a crisis in modern networks, where millions of independent nodes must communicate without ever having met in person to exchange a secret. In a purely symmetric network, every unique pair of users requires a distinct, dedicated key to talk to each other securely. The number of keys grows quadratically. With just 1,000 users, the network has to manage nearly 500,000 separate keys. This creates a massive storage and memory burden. Each individual user in a network of n users must securely store n-1 different keys. At internet scale, manually updating or revoking compromised keys across a network of this size is impossible. Furthermore, symmetric keys cannot provide non-repudiation, the ability to prove exactly who sent a message. Because both Alice and Bob hold the exact same key, either one could have fabricated a given ciphertext. There is no mathematical way to prove which party generated the data. Purely symmetric networks scale too poorly to support global infrastructure. They have the processing speed, but they lack a scalable logic for distributing trust. In 1976, Whitfield Diffie, Martin Hellman, and Ralph Merkle introduced a new approach, asymmetric or public key cryptography. Instead of one shared secret, the system uses a mathematically linked pair, a public key for encryption and a private key for decryption. Alice can now encrypt a message using Bob's public key, which is available to everyone. Once encrypted, only Bob's private key, which never leaves his possession, can reverse the process. This model eliminates the need for pre-shared secrets, allowing the network to scale efficiently. This is possible because of the one-way function. Calculating the output y from an input x is fast and simple, but calculating x from the output y is computationally intractable. In this context, intractable means that even with current supercomputers, reversing the function without the private key would take thousands of years. Asymmetric architecture solves this problem by basing security on mathematical hardness rather than a shared secret. To build these one-way functions, we use specific mathematical problems that are easy to compute in one direction but difficult to factor in the other. Most systems rely on three families of math: integer factorization, discrete logarithms, and elliptic curves. This graph represents the geometric operations used in elliptic curve cryptography. Elliptic curve math provides high levels of security while using smaller key sizes than traditional methods. A 256-bit elliptic curve key provides the same long-term security as a 3072-bit RSA key. But there is a very significant cost. The mathematics required for asymmetric security are extremely demanding on the CPU. Public key algorithms process data roughly 1,000 times slower than symmetric block ciphers. This means we cannot use RSA or elliptic curves to encrypt large files or video streams. Attempting to do so would cause network performance to drop significantly. This leaves us with a technical conflict. Symmetric ciphers have the speed, but can't distribute keys at scale. Asymmetric ciphers can distribute keys, but they are too slow for bulk data. Modern systems solve this speed versus scale conflict using a hybrid crypto system. This is the foundation for TLS and nearly all secure web traffic. Instead of choosing one method over the other, engineers sequence them to exploit the strengths of both. Phase 1 is the Asymmetric Key Exchange. Bob generates his public and private key pair. Alice then generates a random temporary symmetric session key. She uses Bob's public key to encrypt just that small session key, creating an encrypted package. She sends this small encrypted package across the insecure public network. Bob receives the package and uses his private key to retrieve the session key. This exchange has successfully established a shared symmetric secret across an untrusted network, using slow asymmetric math for only a tiny amount of data. Now the system enters Phase 2, Bulk Data Encryption. Now that both parties have the session key, the slow asymmetric algorithm is no longer needed. The system switches to a symmetric cipher. Alice uses the shared session key to encrypt the actual message or file using a high-speed cipher like AES. Bob receives the data and uses his copy of the session key to rapidly decrypt the incoming stream. This session key is ephemeral. As soon as the communication ends, the key is destroyed. Because keys are generated for single sessions, the security of past data is protected. Even if a future key were to be compromised, it wouldn't help an attacker unlock previous conversations. The hybrid protocol is what makes the modern internet possible. It fuses the scalable distribution of asymmetric math with the raw processing speed of symmetric block ciphers.